Okay, sorry. Great. So good afternoon, everybody. My name is Elena Poli, and I'm a PhD student of the theory group of Francesca Ferlaino in Innsbruck. Before starting, I would really like to thank the organizer for giving me this opportunity to be here at ITAMP, representing my group together with my colleagues. So today we already had a lot of talks talking about dipolar gases. From my side, I will try to give an update about our latest results in Innsbruck. Sorry. Okay, it's working. Sorry. In my group, we work with atoms like erbium and dysprosium that have a large magnetic moment. And so, in addition to the tunable contact interaction, these atoms also interact via the long-range and anisotropic dipole-dipole interaction. And the possibility to tune the S-wave scattering length by means of Feshbach resonances experimentally allow us to, to balance the interplay between these two different interactions. And so we can basically work in different regimes that could be contact-dominated or dipolar-dominated. And in particular, in this dipolar-dominated regime, this is the regime in which we can access the supersolid phase of matter. So I will structure my talk in the following way. First, I will recap a bit the results from my group about supersolidity, in particular focusing on the structural phase transition from 1D to 2D supersolids. Then I will talk about dipolar gases under rotations. And finally, I will give an update about possible applications of rotating dipolar supersolids. And in particular, I will show how this system could actually tell us something about a phenomenon that is the glitches that usually happens in neutron stars. So let's start with the first part. This is let's say, there already have been a lot of talks about supersolidity, so I will try to summarize a bit the main properties of this state. So here there's a nice experimental in situ image from our erbium dysprosium lab, in which you can see that basically this is a 1D supersolid. With this, I mean that the system is actually 3D, but it spontaneously breaks the translational symmetry in one dimension, in this direction, and forming these nice 6 droplets. And these droplets are not independent between each other, but they actually share a global phase coherence that can be experimentally detected by studying the interference pattern. So you let your system expand with a time of flight measurement, and you can actually prove that the system share the droplets share a global phase coherence. We know that the origin of this state comes from the softening of the Roton mode in the excitation spectrum of a dipolar Bose-Einstein condensate with a tight confinement along the Z direction, as it was predicted back in 2003, and as it was also experimentally observed in 2018 and 19. And so by tuning the interaction, when the Roton minimum completely softens, and so when the Roton gap goes to 0, the system does not undergo a collapse as it was predicted, as it is predicted by a mean field theory, but it is stabilized by quantum fluctuations that in the theory we can take into account by considering the first beyond mean field effect that is given by this term, that is the Lee-Wang-Yang term. That is repulsive, it is isotropic, and it rapidly scales with the density, and that's why it becomes important when there are these high density region forms that are the droplets. We know that this state is robust against phase scrambling because it kind of activates a rephasing process quite quickly, reestablishing the global phase coherence. And this process can be modeled by a Josephson array model. And we can also, we also know how to produce this state, in particular via two different methods, either by interaction quench, so by basically lowering the scattering length by means of Feshbach resonances, or by directly evaporating into the supersolid state. So this, let's say, the first experimental observation of 1D supersolid was back in 2018 by 3 groups in Pisa, in Stuttgart, and in Innsbruck. And so then the question was like, how scalable is this system? Because the first supersolid was in 1 dimension, so how scalable is this system? So the first intuitive way to scale the system from a 1D chain to something that has a 2-dimensional structure is to release the trap confinement along the transverse direction, such that the system can develop a transverse structure. And we performed some numerical simulation with the Gross-Witajewski equation, and we found out that we realized that if you just release your transverse confinement and you leave all the other parameters constant, actually at a certain point you lose the supersolidity and you fall again into the BEC regime. If instead, in addition to releasing the transverse confinement, you also load more atoms inside the traps, you also increase the atom number, and in particular, if you keep constant this parameter here, that is a measure of a trap density, so if you keep constant the density of atoms inside your trap, like you manage to maintain the supersolidity crossing the 1D to 2D structural phase transition and eventually end up with this nice state with 19 droplets in a circular trap. So this is what we also try to do in the experiment. Basically, by increasing the trap aspect ratio, we observed also an increased atomic aspect ratio in correspondence of the point in which the system starts to develop also a transverse modulation in the transverse direction. And so we could range from a linear chain of droplets to something that is more zigzag or more complex, like this double zigzag, up to basically this nice hexagonal state that is in an almost circular trap. And of course, we can always, as I said at the beginning, we can always check that all the droplets share the global phase coherence by performing time of flight measurement and always benchmarking with the theory obtained for the same parameters of the experiment. So at the moment, I always talk about density modulation and global phase coherence, but another property that we expect from this kind of state is like superfluid properties. And so in particular, we would like to verify directly these superfluid properties by means of the observation of quantized vortices that would be a direct manifestation of the superfluid nature of the system. So the open question we had is, how can vortices nucleate in a dipolar system? And this was an open question not only for this nice supersolid state, but also for simply a dipolar BEC. And so to study this question, to try to answer this question, we decided to take a step back and study rotations first in the non-modulated regime. So this opens the second part of my talk, in which I will introduce how can we actually rotate this kind of system. So if we have a rotating bucket that is rotating with a certain angular frequency omega, and we put a normal fluid inside of it, at equilibrium, this fluid will just rotate together with the bucket. If instead we put a superfluid and we rotate the bucket, let's say, under a certain critical value, we would see that this superfluid, if the bucket is cylindrically symmetric, this superfluid would not rotate at all. And if we increase the angular frequency up to like above a certain critical value, we will see that the system will develop some topological defects inside that are called the quantum vortices. And the number of vortices is proportional to the angular frequency of the system. So if we have a closer look on one of these objects, we will see that these quantum vortices corresponds to, they manifest as density holes that are characterized by a 2π phase winding around the central point. And the size of the core of this object in general depends on the chemical potential. And if we compute like the circulation of the velocity around the vortex, it is quantized. So we would like to obtain a state like this in our dipolar system. So the question is now, how can we actually reach this kind of state? So in the last few decades, a lot of experimental techniques were implemented to create vortices inside systems. The first, maybe intuitive way is really to induce a rotation to the system, for example, rotating a slightly anisotropic trap, and so inducing a rotation to the system that can develop these holes in the middle that are the quantized vortices. Or you can, for example, put a mechanical perturbation to the system, for example, steering an obstacle, and this would create some phase fluctuations that will create some vortices inside. Another technique is, for example, a rapid cooling across the phase transition from a normal to a superfluid state. Or we can also, in principle, one can also directly imprint a phase pattern on your system by using a DMD. And all these techniques were used for BOSE-Einstein condensate with only contact interaction. But as I said at the beginning, in our condensate, we also have dipole-dipole interaction. And so we decided to exploit this property of the system to induce a rotation to it. In particular by using this method that we called magnetostirring. So if we had like a system, like a non-dipolar system in a trap, basically the shape of the cloud would match exactly the one of the trap. If instead we have a dipolar system, and so for example with a magnetic field that is pointing, for example, in the z direction, because of the dipole interaction, also the cloud would stretch in the same direction of the magnetic field. And this phenomenon is called magnetostriction, and it was seen in 2007 in the group of Tillman-Pfau. And basically, it's just a consequence of the fact that since we have dipoles, they favor configuration in which they are head to tail. But this means that if now we tilt the magnetic field, these dipoles would like to align along the direction of the magnetic field, let's say breaking the cylindrical symmetry of the system that was before because of the trap. And so if we then start rotating the magnetic field, the system would follow it. And so we can induce a rotation and we can impart angular momentum to the system by rotating the magnetic field. And this can be done in the experiment by using 3 pairs of coils that can, each one of them is responsible for the magnitude of the magnetic field in each of the 3 directions. If you want to have a classical analog, this is also what happens, for example, if you have a ferrofluid and if you want to rotate it with using a magnet, you will see that these droplets are aligned in the direction of the magnetic field, and if you rotate the magnetic field, they will just follow it. So we expect that this method would impart angular momentum to the system. And in particular, what we expect is that for increasing values of the rotation frequency, the system would elongate more during the rotation until it reaches a dynamical instability at a certain frequency. And this dynamical instability is the seed for vortex nucleation. So it's the seed to have vortices inside the system. So to study this, we first decided to do some simulation to understand which were the best experimental conditions to observe this. And in particular, we decided to study the stability of the system, since we want to see when the system becomes unstable and when we have vortex nucleation. So we studied the stability of the state depending on the tilt angle of the magnetic field, the initial tilt angle. What we observed is that for small values of this tilt angle, from 0 to 20 degrees, the aspect ratio of the system increases not so much, and then basically it goes back to 1. So we don't observe, so this is like the state at the beginning and this is the state at the end, and we don't basically observe any vortex in the middle. For intermediate values of this angle, actually, we see that the aspect ratio of the system increases, it reaches a maximum, and after that it basically collapses again. So this is the moment in which the system undergoes the dynamical instability, and after that we have vortex nucleation. You can see that there are holes in the middle of the system. If we increase even more the tilt angle, basically we are the attractive dipolar interaction of the atoms that now are even more head to tail is so strong that it suppresses the dynamical instability. And so you see that the aspect ratio keeps increasing, but it does not collapse. So from this analysis, it's quite clear that this middle range is the best one for the experimental, to observe this dynamical instability and this vortex nucleation experimentally. Here you can see that these are some experimental points obtained for this specific value of the angle. That is the one that we used for the next results that I will show. And in order to optimize the time for vortex nucleation in the experiment, we decided to rotate the system at a frequency close to the value of the dynamical instability. So without doing this ramp, we just set the frequency of rotation at this fixed value. What we expect is something like this. So here there's a simulation in which we tilt the magnetic field and we start rotating at a constant frequency that is something like this. So first you see that the dipolar BC gets elongated as expected. Then it's spiralized somehow, and here you can already see that so first there are some quadrupolar deformations at the beginning, and then you see these holes, and so these vortices in the external low density region. So they are created and they slowly start to enter inside the system. Here you can see that the vortices are trying to go inside, and this is the moment in which the aspect ratio of the system that first was really elongated, it basically goes back to 1. Okay. So this is a simulation, and here there's the comparison between simulation. Basically, these are just some frames of the previous simulation that I show with the experiment, and you can see that there's a good agreement for the same time scales. So first there's this spiral, and then you can see that there are vortices, and vortices enter, and the same you can see here. Here there's the spiral with some. Then start to see these holes, and these holes go basically inside the system. In experiment, we have atom losses during the rotation, and so that's why the size of the cloud is smaller, in particular at the end, compared to the one of the simulation. So one peculiarity, so there are some peculiarities for vortices in dipolar systems. In particular, when the B field, when the magnetic field is in plane, we expect the vortices to have an elliptical vortex core, just because of the dipole-dipole interaction. We also expect that around the core of the vortex to have some density ripples, in particular if we are close to the if we are in the close to the Roton instability point, and then, in particular, we also expect to have an altered vortex lattice. So instead of the triangular lattice that we have in contact-dominated BC, we expect to have this stripes configuration. So the vortices aligned in stripes instead of a triangular configuration. And in particular, we focused on this last property. And what we observed is that This is like the ground state of the system in the rotating frame for the same parameters of the experiment. So when the magnetic field is in plane, so it's still tilted. And these are some experimental results, and these are the simulations for the same time scale. And so if you like plot the residuals that are obtained by subtracting to the density, like the blurred density, in order to see a bit better, and we use this method to detect the position of vortices. So you can see that these vortices are kind of aligned. They have this preferential direction that is more visible if you perform a Fourier transform of the residual, because you see the presence of these two peaks in the K-space that resembles the periodicity in stripes in the space, in the position space, or in the residual. If you then tilt the magnetic field in the Z direction, again, you lose this feature because you basically restore an isotropic vortex distribution, like that you can see here in these two cases. So again, experiment and simulation. And this is quite clear if you perform the Fourier transform, again, of the residual, in which you see this ring that really resembles that now you don't have any preferential direction anymore. So all these results were obtained for for the non-modulated state. But as I said at the beginning, we would like to extend these results also to the supersolid state. And so in the theory, in particular, we would like really to apply the same protocol to just a state that is obtained by lowering the scattering length. And so in particular, we would like to tilt again the magnetic field and rotate it, so as it is in this simulation. So we expect the droplets to follow the rotation, and so we are inducing a rotation to the system, and as you can see from the phase, here at the end, after a certain amount of time, there are, for example, here 2 vortices. And one important thing is that the critical frequency for to have vortex nucleation is expected to be lower than the one that we have in the BC, because the energy barrier that the vortex has to overcome in order to be inside the system is lower because of the lower density region in between the droplets. And so, notice that here the frequency is, before it was 0.75, it's 0.25. So here there are some experimental results in which you can see that by tilting the angle, we are actually also tilting the droplets that align along the magnetic field direction. And here you can see that if you rotate the magnetic field, also the droplets would follow it. So we managed to rotate a supersolid state with the same protocol that I showed you before. Now there are 2 main challenges. The first one is that when you produce vortices inside the system, they will stay in the low density region in between the droplets. And so the question is, how can we actually detect them? And second, is the lifetime of the supersolid, in particular during the rotation, long enough to observe a vortex nucleation? So to try to answer this question, we follow this theoretical proposal from the group of Stringari in Trento. And so in particular, they say that if you manage to produce a vortex in a supersolid state, and then if you quench the scattering length in order to cross the supersolid to BC phase transition, this vortex should remain, so if you have a vortex here, the vortex should remain inside the system. And once you are in the BC regime, you are able to detect it, as I showed you before. So here there are some preliminary results that we obtained very recently, in which you can see, so this is the protocol that we applied. So basically we rotate a supersolid in the way I showed in the previous slide at this value of the frequency. Then we spiral up the magnetic field and we perform this quench into the BEC regime. And what you can see is that you see that the system has a null in the middle. This is for 3 different time interval of rotation. So this is obtained for different time. But the result is the same. if instead we apply basically the same protocol, but rotating at the same frequency, but in the BEC regime, so we do not observe any vortex nucleation. So like, because this omega is too low to produce a vortex nucleation for the same time scale. So these are really preliminary results. We are still producing these, and we are still analyzing what we have. But like, it seems that very, very promising method. And in particular, also we can answer the question about the lifetime, because it seems to be sufficient to observe such kind of vortex nucleation. Okay. For the last part of my talk, I will explain a theoretical project that is basically an application of rotating dipolar supersolids. In particular, to observe glitches phenomena that are phenomena that usually are seen in neutron stars. So for this reason, let me start with a very general introduction about neutron stars, in particular, what are the main properties that we need to know to understand the connection with dipolar supersolids. So neutron stars have a gravitational mass that is 1 or 2 times the mass of the sun. They have like a small radius, usually it's around 10 kilometers, and the temperature are like orders of magnitude lower than the typical energy scale of nuclear matter. So because of these properties, they can be viewed as very dense and called the nuclear matter system, in which quantum effects are important. So how do we see them? Usually we see they manifest as pulsar, so they are like highly magnetized rotating neutron stars that emits an electromagnetic radiation out of the magnetic poles that they have. And since the rotation axis and the magnetic axis are not aligned, but they are misaligned, from Earth we can see them like as a lighthouse effect. And so this allows us to basically measure with like very high precision the rotation frequency of the star according to the measure in which they are off pulse or on pulse. So you see really this lighthouse effect from Earth. So since it's rotating and it is emitting radiation, so we expect that this object would lose energy in time, and so also the rotation frequency should the rotation frequency should decrease in time. But every once in a while, you observe like that this spin down is interrupted by a glitch. So this is a glitch, and this is like this discrete and randomly timed jump in the angular velocity of the neutron star. And these jumps are quite small. They are of the order of magnitude of 10 to the minus 12 to 10 to the minus 3. And the widely accepted mechanism for this phenomenon is believed to be a consequence of the internal dynamics. And in particular, it's believed to be like a hint of superfluid properties of neutron stars. So let me give a very general idea of the structure of the neutron star. So in particular, like this is a section of the internal structure of a neutron star. The outer crust is believed to have a crystalline structure, so solid properties. The heart of the neutron star is the core, and it is believed to have superfluid properties. And in between the two, like the inner crust is believed to have a coexistence of crystalline and superfluid properties. So you can see like this is from this paper, they analyze like the structure. You have this the presence of these crystal sites, but they are not independent because like they are connected by this neutron superfluid bath that connects the crystal sites. And so this resembles a lot, it's very reminiscent of the supersolid phase that we have, in which we have these droplet sites that are connected by this like superfluid background. So going back to the neutron star, like the accepted mechanism to see these glitches, so this is sudden spins up of the neutron star that is basically normally slowing down, is that, okay, so as I said before, the outer crust is a crystal, and so it rigidly rotates at the observed rotation frequency. And the inner crust, because of these superfluid properties, it will lags behind. And so, it also will store angular momentum in form of quantized vortices that, because of the presence of the lattice, will be pinned in specific positions. Then, during the slowdown process, the inner crust would lag behind until it reaches an out of equilibrium state. After this out of equilibrium state, it will release like a sudden amount of angular momentum through a collective unpinning of vortices. And so this angular momentum that is released from the inner crust, it is absorbed by the outer crust. And this causes the sudden spins up of the glitch. So this is like the reason for this sudden spins up that I showed to you before. So since the inner crust resembles a bit the structure of dipolar supersolids, and since these glitches this inner crust is responsible for the glitches phenomenon, we can try to use dipolar supersolids as inner crust laboratories, so to simulate exactly the same dynamics. For example, we can take like this supersolid state with 19 droplets, and we can put it under rotation. So we can create our state in equilibrium in the rotating frame. It will host quantized vortices that you can see here from these holes, or here in the 3D version, these are like the vortex tubes. And these vortices are pinned in specific positions because of the presence of the droplet lattice. So as in the neutron star, we can simulate the slowdown process with a dissipative extended Gross-Pitaevsky equation. And most importantly, unfortunately, I don't have the time to go into the details, but we can implement a model for the feedback. So with this model, basically we are saying that during the slowdown process, every time that the supersolid loses a vortex, its angular momentum is reabsorbed by the solid part of our supersolid. So with this, basically by solving in real time these two differential equations that are coupled, because the result of this differential equation is omega that then goes here, we obtain, for example, these results. So this is like our supersolid with the vortices. Now, if you focus on this, so a vortex is leaving, another one is taking his place, and also you have other unpinning of vortices, and this corresponds to the point in which omega, that is the rotation frequency, suddenly spins up. Now, again, if you focus on this vortex here, this leaves, the other one takes its place, also this other one is moving, so it's not an effect due to only one vortex, but it's something more collective. And again, you see that the omega spins up, and then you have this oscillation here. I will be back on this oscillation later. And here again, if you focus on this one, we have now our third glitch. And again, the same phenomenon, the same spins up. So, I mean, these jumps are quite small. But if you look at the order of magnitude of delta omega over omega, that is the same quantity that I showed to you before for the neutron stars. So this is the order of magnitude. This has an order of magnitude of 10 to the minus 3. So it would be like a giant glitch compared to the numbers that we have in neutron stars. And like this model seems to be quite promising for the fact that we can't have access to the internal structure of neutron stars. But here we managed to really replicate the same physics. And here we can really have access both to vortex dynamics, to understand what is the unpinning mechanism, so what happens, and also to crystal excitations, because our crystal is not fixed, it does not co-rotate with the trap, but it's made of droplets, and these droplets are perturbed every time that a vortex goes out. And so we would really like to analyze like the shape of the glitch, and in particular the frequency of oscillation, the size of the glitch, and relate it to this crystal excitation, because maybe for neutron star, by looking at the size and of the structure of the glitch, we can infer something about the internal structure or the lattice that we can have inside. So with this, I come to my conclusions. I showed you how like the experimental realization of two-dimensional supersolidity opens the new possibility to have like a direct probe of the superfluid nature of the system. I showed you how magnetostirring offers a unique way to impart angular momentum to a dipolar system. And finally, I showed you how rotating dipolar supersolids offer the possibility to test both the vortex dynamics and the crystal dynamics during a glitch, in analogy to what happens in neutron stars. I would really like to thank all my team and also the external collaborators for all this project that I showed to you. And in particular, so Tom, Lauritz, and Wyatt are here, and they will present a poster. So if you are curious to know more about other projects we are working on, or more about vortices, in particular about experimental details, I think they will be happy to answer all your questions. And last but not least, I think Francesca, Antoine, and Robert are organizing this conference in San Sebastian in September. It's about long-range interaction, so she thought it was a good moment to advertise this event to you. And thank you for your attention.
Thank you very much, Elena. So, questions?
Thanks for showing us nice results. I was wondering, the time between glitches, what does that exactly depend on?
Yeah, that's a good question, because you can't really predict when the system will go in this out of equilibrium state, because the thing is that, because of this superfluid character of the system, it will a bit lags behind compared to like the ground state of the system for that specific value of the rotation frequency that you have. So yeah, I think really the glitch is defined to be something that is like randomly time distributed. So
it looks like they come like in similar distances. Is that true? Or?
Yeah, it's not. I mean, yeah, it's not true. It's not true in general, I would say. I mean, I think I have. Wait. I have. I don't know if I put. Sorry. I don't know, I have other results here for different scattering length, but like, for example, here the time scale is much longer than this true. So yeah, it's not. Yeah, yeah, exactly. And also, yeah, please.
Thank you. This is all cool stuff. I mean, I have a question about the neutron stars as compared to this. I mean, yes. Here you see that quantum by quantum is absorbed by the solid, and then you see basically one vortex at a time.
Yes.
Leaving the system. Is this also true for the neutron stars?
No,
because I mean, one quantum is probably such a small quantity that
so
you cannot detect it. So how does it work there? That basically, do they like team up and have some whatever collective process that thousands of vortices or many more leave at the same time? Or how can I think about this?
Yeah, so in neutron star, I think the number of vortices that is expected to leave is like 10 to the 7 for each glitch, because like the time scale is completely different. What we managed to simulate here is like one vortex leaving or two vortex leaving. So in this case, this other simulation, we also have two of them leaving, and other inside that are moving. And so since they are moving at a different radius, the angular momentum is redistributed. No? So like it's still a collective thing.
But can you imagine, also looking at your simulations, that the distortion due to one vortex that is left behind sort of makes it easier for other ones as well, and so on.
Yeah, exactly.
And but okay, 10 to the 7. Yeah.
Yes,
wow.
but yeah. Yes.
Okay, thanks.
Very nice talk, very interesting. So, just wondering, for measuring this change in frequency, what would you do in the experiment? I mean, how you that you let the system expand? What would be the way to do it?
So you mean for the glitches?
The
for
delta
this?
omega.
Yeah, so okay, at the moment, this is like a theoretical proposal, also because of this model for the feedback. So in principle, you would like to, because at the moment now we are like say, okay, the angular momentum that is released by the vortex is kind of reabsorbed by the solid part of our system. So there is this model behind that, I mean, it's not trivial how to implement it in the experiment. I think one thing we thought was to like extend these to two-component systems in which one of the two components drags the other one, and so you would be able to measure, you know, like the angular frequency of the other component compared to like the relative frequencies between the two. But yeah, at the moment we don't have like a clear answer for that.
So regarding the vortex nucleation that you showed, have you seen vortex melting at all?
You mean annihilation?
Yes.
No, because they all have the same like vorticity with the
So you
same.
don't
They are
have-
all the same sign because we are rotating the magnetic field always in the same direction, and they have all the same.
So they remain robust.
Yeah.
Okay.
Yeah.
And what are the quantum effects of these vortices compared to the normal vortices that we know from superfluids?
What do you mean? Sorry, like.
I mean, so here you have, let's say, the quantum fluctuations, right?
Yes.
So what is the difference between the vortices that we know from normal superfluids? Do they differ in their core size? They are more
You
shallow?
mean super solid phase and normal superfluid phase?
Yes, the vortices.
Yeah. Yeah. So I think the one difference. So they are the same. They are the same topological defects. The circulation is still quantized. The angular momentum that they carried is less than 1 h bar. Like it's less in general. So this is one, I think, the main difference. But I mean, they are the same topological defects, topologically protected. So yeah.
And did you try to do this trick of rotating at a smaller frequency and then changing the scattering length, entering into the supersolid, and getting the vortex? As
You
we
mean
studied
the
with
opposite,
Sandro?
like?
So basically, not only just the trick of quenching into the supersolid as a way of seeing the vortex, but as a way of nucleating the vortex.
Nucleate? No.
Because in that paper with Sandro, basically, we have these two parts basically, in which you quench at the same time as you rotate, so to say.
Yeah.
And then in this way you see this less than h bar, as you say. Yeah.
Yeah. I see what you mean. Yeah. No, at the moment we are just. I think we are just rotating the supersolid, trying to create a vortex there, and then just quenching just to see. To detect what we actually created before.
And just one question, because I have 1 minute. So, in the way of rotating just with the dipole, so to say, the pictures that you showed before in the non-supersolid regime, you create many vortices. So it's a kind of very violent effect in some sense. Is there a way to is it possible to do this rotation with the dipole and at the same time creating just one vortex?
I think so, yeah.
Is it as controllable as just rotating the trap? That's my...
I mean, okay, so all the movies I showed before and all the pictures, so first it's rotating at a frequency that is 0.75, the trapping frequency. So of course, rotating at lower frequency would reduce the number of vortices, but it's also true that it would take more time for vortex nucleation. So I think we decided that because like it was faster enough. So in principle, yeah, you can control it, but it would take like more time to reach it. Yeah.
Okay, so quarter. Yes, very good. Thank you.